welcome to the 8th Open Sky Symposium. We would like to present our project entitled Automatic Call Sign Detection, Matching Air Surveillance Data with Air Traffic Spoken Communication. This is a project financed by Clean Sky and also the European Union. So these are some highlights that we would like to present in this project. So first, we would like to present what's ATCO2, also the main challenges in speech recognition and also call sign detection for ATC communications, in ATC communications. So also we would like to share our standardization and data collection process for ATC speech and also radar data. We would like also to present the deployment of the first VHF receivers in different airports and also countries. So the main idea is that ATCO2 is approach to use also context information such as radar from OSN servers to increase the performance of the call sign detection system. So we are introducing a state-of-the-art speech-to-text technologies for ATC. So this is a brief outline of what we are going to see today, going from introduction, problem, previous projects, conclusions, and a bit of bibliography. So first of all, ATCO2 is an EU project. The main goal is to collect, organize, and process air traffic control audio data. So we are targeting the communication between pilots and air traffic controllers, or ATCOs. And also, we would like to get metadata, like from the OSN servers, to improve the performance in our systems for speech to text and also to call sign detection systems. So first of all, it's good to mention that ATC speech is not an easy task because there are many variations due to the speaker, for example, stress, fatigue, inter-speaker variations. There are different accents of the ATCOs, also the pilots, dialects. Also, this speech cannot be like classified as a spontaneous speech because it's not a conversation. Also, it's not they are not reading, and also it's not pure command because there are some deviations. So we need to take all of those things into account. Also, there are different ATC scenarios, for example, clearances, arrivals, takeoffs, all of that information, all of the scenarios we would like to target for call sign detection. So there are some previous projects that have targeted the same goal. Two of those are Mallorca and Glisan. So they were used, but there were some limitations at that time. The first one is that they were just targeting ATCO speech, not pilot speech. Also, they were using just a limited amount of training data, less than 100 hours normally. So, and the data was coming from a few airports, not general, like different airports from different countries, and like creating a system that could generalize to different accents. For call sign detection or just for treating ATC speech. Also, it's important to mention that the ATC communication follow the ICAO regulations. So there is normally the messages, there is one call sign, the airplane, and also one command that's in normal condition. But we have seen some deviation, and that's also something that ATCO2 wants to target. So what we would like to solve is that transcribe this data is very expensive, needs very high people working a lot to produce or to annotate this data. In fact, just to create 1 hour of speech without silences requires 1 man week work to create this. So it's very expensive and it takes a lot of time. So the first phase that the ATCO2 is targeting is the first we have collected some public ATC data from live ATC, which is normally quite noisy because they are using some receivers that they are not like the best quality for that. So we have seen that. So the second phase of the project is also to design, build, and deploy our own VHF receivers to collect our own data, and also to try collect data from different airports, different locations across Europe and also around the world. So also the idea is to generate those transcripts for the data that we are collecting. And what we have done is that we have correct those transcripts in order to create a set that where we can evaluate our system. for call sign and also for speech to text. So this is more or less what ATCO2 is, the whole overall of the project. The green area at the top are normally what has been done before. Normally people, the previous project, what they have used is that they have gotten good quality data. Normally that's high SNR, and also, but normally they are constrained to just a few hours, not more than 100 hours or in most of the cases. So what we are doing is that, what we like to do is that we can use these VHF receivers to get data. We can, normally this is a bad quality data or low SNR data, but we can collect a lot of data. In fact, we have collected almost more than 1,000 hours of ATC speech. So the idea is to also, we know that from Open Sky Network, we can get air surveillance data from a DSB and also Mode S. So the idea is to get that air surveillance data and match, timestamp that air surveillance data with the data that we are getting from the VHF receivers. So we get this from the VHF receiver. We know when was recorded that specific recording and also where. So we can send that to OSN to get some list of call signs that match that search area. So the idea is to use that information plus our speech to text system and also call sign detection system to get a call sign in the ICAO format. But also more important is to use the radar and air surveillance data to generate better to get better accuracies. So what we have done so far is what we have gathered 195 hours of ATCO speech, annotated, normally good quality. What we have recorded also some data from VHF receivers. We have cleaned it. We have trained some systems, and we have done some pre-processing. And the idea is to unify all that data, almost 200 hours of data. Like unify in the same way of the transcripts are done. Also, we have applied voice activity detection, diarization to see whether this is an ATCO or pilot. And we have trained a language model and acoustic model, state of the art, like with techniques that are state of the art currently for speech to text. And also we have fair result for call sign detection from these given transcripts. So what we can do with surveillance data. So the main target before, like as explained before, for ATCO2 is to extract the call sign from a given neutron as a given recording. Could be a recording between a communication between an ATCO and a pilot, or pilot, ATCO pilot. So initial solution is to use a speech to text and text to call sign system. But previous results, we have seen that there is good performance, but only just in good data, good quality data, like the one provided by air navigation service providers. But the new target of ATCO2 is to improve the performance also not just in good, but also in bad quality data. So then we can accept, I would say, or we can transcribe data coming from different airports, different countries, and so on. So the solution is to use OSN servers, air surveillance data, to increase this. So we can use it either in the speech to text system, either also in the text to call sign system, or in both. So the idea is to see how can we put that information, how can we mix or add that information into the pipeline to create a better system. So the expected result is that we are expecting much better accuracies and performances doing that. So the idea is we first gather an ATC segment with a VHF receiver. We have the metadata, that is the location and the location of the receiver, and also the time that when it was taken. So we record that information. We send a query to the OSN servers. We retrieve some list of call signs in the ICAO format, and then we do some verbalized transformation to transfer the ICAO format to a verbalized way that where we can compare with the previous databases that we have gathered so far. But nevertheless, we have seen that there are some non-standard abbreviations. So there are also deviations per call sign or deviations in the communication. For example, the initial contact normally should be the full call sign, but after abbreviation are allowed. So we need to train a system that it's capable to recognize that, or like a prone to those deviation. So how we do record our own data? So first, we use the wideband scanner and also an antenna, and also a recording software called RTL SDR Airband. So we gather the data in raw format, and then we can pre-process that data. So we have tried different setups, like expensive, more expensive antennas, cheap antennas, in order to see how the quality of the record data is impacting the system. So for example, in fact, we have seen that there is almost 10% different in error rates just by using a better setup. So the idea is to see to find that threshold between expensive and not expensive setup, and the information that we can add into the pipeline from OSN. So just to clarify, speech to text system is also called ASR, which is automatic speech recognition. So how we produce transcript from speech. So first, this is one of the main components of the overall pipeline, because we need to know what has been said in this specific recording, and then we can work with that text data. So first, we get as an input the audio signal with the speech of ADCOs and pilots. So the output, or the expected output, is the hypothesized transcript. So either way, the transcript could be the best transcript, like the more likely transcript, for example, Lufthansa 123, or a lattice with some alternatives, for example, Lufthansa 123 or Lufthansa 124 or Lufthansa 125. So this graph can have that weighted, like let's say, like path. So the challenge is to use context information to increase the performance of recognizing these call signs, and also get the transcription of a given utterance. So this is more or less how it looks like. So we have the spoken communication we can say that has a call sign and a command. This is our private information. So from that recording, we can get some metadata. That metadata is the location and timestamp, and then we send a query to the OSN server, and we get as a retrieve, like a list of call signs. So the speech to text system has the best transcript. It can be like Ryanair 175, or like an encoding graph that says that it could be Ryanair 165 or Ryanair 175. So the idea is that if we know that Ryanair 175 is not the right one, we can use the list of call signs to narrow somehow the search space and give more weight to the call signs that we are getting for OSN, because we know that these transponders or the information that the airplanes are sending to OSN are like ground truths, or we know that that's true. So with this, we can, fusing that information, we can increase the performance. So we have two systems that we are proposing: is the hybrid approach for speech to text and also end-to-end approach. Both are state-of-the-art systems, and they are, we are using the state-of-the-art approaches for speech to text systems. So the hybrid approach, you have the lexicon and also the acoustic model and also the language model, and they can be trained separately. So normally those are based on HMM, which are hidden Markov models, and also deep neural networks. Normally they are more complex, but they allow more freedom, because you can tune somehow like intermediate steps. Normally it requires less data and generalize faster. The end-to-end approach, it's like the lexicon and the language model and the acoustic model, and train jointly. Normally they are less complex, but there is less freedom because you cannot tune in between, and they require more data. So yeah, as mentioned previously, we have gathered almost 200 transcribed data from other databases. We have add noise that is related to live ATC audio. So we know that is noise that are present in the recording. So this is like a data augmentation targeted to this specific database. We have seen that it helps a lot, almost 10% in accuracy. So we have some test sets. We have so far one test from Airbus database, from an Airbus challenge. We have two test sets from Mallorca, EU previous project. We have three test sets, two of live FTC, which we know that they are more or less bad quality, and we have also from LKTV Airport, which is a little bit better quality. So for the text-related pre-processing, we have unified different vocabulary. For example, the ICAO alphabet. We have standardized the word splitting. For example, you can see takeoff, and also the designator for different airlines, and we have prepared an external data of OSN flight lists and also all possible runaways and waypoints in Europe. So we have added that in the language model in order to at least that being present in the language model, so the system can generalize better to different deviations or different data coming from different airports. So far we have this result for the proposed databases. We have both for hybrid and end-to-end system. We can see that Airbus and Mallorca, which are better quality system, they yield a better accuracy, which is this is word error rate, normally closer to zero the better. So for example, for live FTC we have more than 30% word error rate. For LK, so there are some quick takeaways that we can see from that table. So first, the better recordings, better system that to record that data, the better the performance. So we have seen that also there is a drop in performance for live FTC, which is a poor or not as good as, for example, LKTV recordings. So what we have seen is that we can boost the system with OSN, or we can say local words, to that test set that are verbalized calls and retrieved from ONSN for that given transcript. So we can do two type of boostings, a priori or SPOCs. A priori is that you have you can do some you can give some score discount to certain words and phrases or call signs, and the idea is to increase the chance that the speech to text system at the moment of decoding it will output the correct phrase. And in the exposting is that the system works, then decode, and then create like a lattice or with alternative pronunciations, alternative output, sorry, and from there you can narrow the possibility of those path or splits by using this OSN information. So we call this boosting. So we have seen that these are the results for boosting. We have seen that using boosting we are getting almost 3% increasing word rates for live FTC set to that, which are the most recent test set that we have gathered. The problem is that it takes some time to create this boosting or to apply this boosting, and after that it cannot be used per utterance, so it needs to generalize to some set of utterances. We can say that it can generalize to one airport or one country or something like that. So, but we know that this is working, and we know that we are going in the right way. So we expect much better result with more targeted experiments. For the call sign identification system, we have the detection module. It's a detection module based on transformers. Which are a state-of-the-art system for this type of tasks. They are based on BERT, which is a specific architecture of transformer. So this is a sequence labeling task. So we have an input sequence, which are transcripts, and we expect an output sequence, which are call sign from that transcript. So the format that we are using is IOB. So I stands for inside, O for outside, and B for beginning. So for example, we have these utterance, which is that. So the idea is to be, it will put when it's beginning the call sign, and I would say like this specific token or word is belonging to the call sign, and O, that means that it's not belonging to the call sign. So if you are wondering how the call sign detection model works, or you are thinking like a better explanation is like this. Imagine that you have an encoder system and a decoder system. So the input to the encoder system is the whole utterance. Obviously, the system has been previously trained with these like labeled transcripts. So the encoder, you pass the whole transcript, and the idea is to retrieve this kind of IOB format, and then from that you can filter out what is not part of the call sign, and then you can get the call sign. That is that one, KLM27 Yankee. So for the call sign detection model, this is also is called name entity recognition. So we download the weights of a transformer BERT, and then we fine tune that on this specific task. So it was a like this is the right way, because we don't need to train the system from scratch, and we don't need too much data to make the system start understanding, like start like getting the idea of how to do this task. So far we have done that just on Airbus data, because we have that data, and because also the training set provides the transcript and also the call sign per each utterance. Well, we have also tested the system in live FTC, but the problem is that here the system is with the ground truth transcript. So that means that we are telling to the system that we are passing to the system the ground truth transcript, which that means that those transcripts are got from the best speech to text system. So we are working on getting the results with the output of the speech to test system. So maybe we can say that we would like to present, or that will be like the full pipeline of the system. So those are the performances of like FTC and Airbus. So as a recap, we introduced ATCO2 and the main goals. We are working on improving our call sign detection system. Also, the context information from OSN helps a lot. And also we present each subsystem, like the data recording, cleaning, the VHF receivers, how we pass that data to the system, then how this speech to text system produce the transcript, and then how those transcripts are used to get the call sign, which is the text to call sign system. Also, we believe that when adding to the text to call sign system this context information, we will get much better results. So well, this is the end of the presentation. If you have any questions or suggestions, I would be happy to answer. Also, those are some references. You can go to our manuscript and find much more references. Thanks.